Okay, this is going to be part 2 of the video series on the alternating series test. And if you haven't done it yet, I would definitely take the time to watch the first video, and it explains a little bit about where this rule came from. In this case, we'll primarily just work some additional problems, but let's begin kind of where we left off in that first video. So here's the definition, and it says that if you have an alternating series and you want to show that it converges, you can show that it converges if these two conditions are met. And the first condition says that the terms of the series have to be approaching 0. Second condition says that any term in the sequence has to be less than the previous term, which basically means that the sequence has to be decreasing. So the idea is, given an alternate or alternating series, execute these two tests, and if they're true, then the series converges. So let's try one of those. And again, we'll go back to the same problem that we looked at on the last video, but let's just rework this one again real quick. So what I'm going to do, I want to know, here's an alternating series, does it converge? And again, the first thing I will do is go down here to, let's see. Okay, I'll make this be the summation from n is equal to 1 to infinity of, and I'm going to rewrite it again as -1 to the n, and I'll take this 1 over n and move it over here to the outside. And again, what that is, I think I'll put it in red, that is going to be a sub n. So this just makes it look kind of like the rule. Here's the switch that alternates it between positive and negative, and this is it. And it looks like this right here. So there's a sub n, and there's the switch. Now, what the rule says is I need to find the limit of the sequence as n goes to infinity, and I'm hoping that it approaches 0, so I'll test that. So the first test will be this. Let's see, I'll come over and make this will be the first condition. You want to show that the limit of a sub n as n approaches infinity is this thing equal to 0. So in this case, again, it was pretty easy to do. We'll take the limit as n approaches infinity of 1 over n. And again, as n goes to infinity, this entire term would go to 0. So that limit does go to 0. So this is true. It passed the first condition. You're okay there. So now, since it passed the first condition, let's go back after the rule, and you need to test the second condition. Is any term less than the term in front of it? So what this one says is a sub n plus 1 less than or equal to a sub n. And all that means is everywhere you've got an n, replace it with an n plus 1. So this would become 1 over n plus 1, and I want to show that that's less than or equal to 1 over n. And you use the same arguments that you guys have used in other tests. If you have a denominator, if the denominator is n, and this denominator is n plus 1, then the denominator on the left will always be bigger than the denominator on the right. And the one with the bigger denominator gives you the smaller fraction. So in this case, the fraction on the left is less than the fraction on the right, and this is true. So what this means is it passed the first condition, it passed the second condition, so you can conclude that the original alternating series converges. So the original, and we'll call it alternating series, does converge. So that one turned out to be pretty straightforward. It passed the first two tests, and you've got it. Now, for the next test, let's take a look at this. Suppose we got a problem that looks like this. We've got an alternating series, 3n over 4n plus 1. Now, before we go on to that, let me go back, and it's worth taking a look at a relationship here. As it turns out, the alternating series test is kind of related to the nth term test for divergence in the following. Now, look at this first step here. When you check this condition, you're checking to see whether or not the terms of the sequence approach 0. In this case, you're hoping that they do. But anyway, the check is, are the terms in the sequence approaching 0? Now let's switch over and look at the nth term test. So the nth term test for diversion, it actually asks you exactly the same question. Are the terms of the sequence approaching 0? Now, when you did the nth term test for divergence, you were hoping that the terms of the sequence did not approach 0, because if they didn't approach 0, you knew that the series diverged. So in the nth term test, you're evaluating this limit, but you're hoping that it turns out to not be 0. But in the alternating series test, you're doing exactly the same thing. You're just hoping that it is. Now, the reason I bring this up is that anytime you execute this first condition and you evaluate the first condition to see whether it's true, you're actually simultaneously performing an nth term test for divergence, because either this limit's going to be 0 or it's not going to be 0. So now with all that, let's take a look and see how that affects this next problem. Okay, we'll get rid of this. Okay, so it looks like this. Now again, what will happen is, let's go ahead and we're going to go back through exactly the same 2 steps. I want to first of all see whether the limit exists and then see whether it's decreasing. So in this problem, again, the actual sequence is going to be this group right here. So this is going to be A sub n. So my first step is to figure out whether the limit of A sub n as n goes to infinity is equal to 0. So that's going to be the limit of 3n over 4n plus 1. As n goes off to infinity, what's this thing going to do? Now in this case, it's pretty easy to do because this is a polynomial divided by a polynomial. And remember the rule. If both the n's are to the same power, then the limit is just the ratio of the coefficients. So in this case, this will turn out to be 3/4. Now what this is, the limit turned out to be 3/4, which is not equal to 0. So what this means is that this condition right here is not true. So I evaluated the first condition and it turned out to be not true. So let's go back to the rule. If you evaluate the first condition and it's not true, all that means is that you cannot use the alternating series test. So at this point, you have to stop working on the alternating series test. So again, as soon as you know that it's not true, I'll put can't use the alternating series test. So you can't use the alternating series test to show that it converges. But actually, you've got something done. What you've done is you can do this. When you try to find this limit was not equal to 0. So let's go back, and what you in effect did was this. You actually executed the nth term test for divergence. So you tried to find the limit was not equal to 0, therefore the series diverges. So at this point, you can go back and make the claim that this series is going to diverge, but now here's an important difference. It's not going to diverge because it failed the alternating series test. It's almost like you can draw a line across here. Once that limit was not equal to 0, you're no longer looking at the alternative test. You've switched to the nth term divergence test, and the series diverges by the nth term test for divergence. So the nth term test for divergence. So the idea is you started out with the alternate series test. When you tried to evaluate the first condition, that first condition turned out to be not to be equal or true. It turned out to be something other than 0. And therefore, you have to stop using the alternating series test and switch to some other test. And the test to switch to would be the nth term test for divergence. But again, you've already done that because this first step really is, it's a combination of both the alternating series test and the nth term test for divergence. Again, what does it mean when you get this? Let's just do a quick little look here. If I were to graph this, it would actually look something like this. The reason the sequence will converge if it settles on a fixed number. But if the limit is going to 3/4 and you still got this plus or minus 1, it's almost like you have a plus or minus on the end of this. So what will happen is here is 3/4. Here is a minus 3/4. And if you go way off to infinity, this thing is alternating between, you kind of put a little dotted line like this and a dotted line like this. Then if you go way off to infinity, it's like it's plus 3/4, minus 3/4, plus 3/4, minus 3/4, and it never does anything in between. And over here, it might look something kind of like this. It goes up like this, but it settles in on that. So it just alternates between a positive 3/4 and a negative 3/4. But in any event, it diverges. So again, if you try the alternating series test, and the first condition leads you to a limit that's not equal to 0, then that means you can no longer follow up. You're done with the alternating series test. But that also means that it did an Nth-term derivative or Nth-term test for divergence, and in this case, the limit was not equal to 0, so you showed that the original series diverged. Okay, let's try a couple more. Okay, now in this one, it's going to be a little bit different. We'll run through the same things again. I've got this, and I'm going to go ahead. My first step again is to rewrite this as the summation as n equals 1 to infinity. And I'll leave the -1 switch over here to the side, and I'll rewrite this as 5 over 4n squared plus. Now again, this is the series, or the sequence. So that's going to be a sub n. So what my two tests says are, again, first of all, show that the limit is equal to 0 if I can. So let's try that to start with. So the first condition, you want to show that the limit of a sub n as n approaches infinity is equal to 0. We'll put a little question mark here because we're not sure if that's true or not. So go ahead and do that. Find the limit as n approaches infinity. Now again, just the sequence part of it. You don't have to worry about the switch. Of 5 over 4n squared plus 3. Again, remember from your limit rules, if the power in the denominator is greater than the power in the numerator, as n goes off to infinity, the entire thing will go to 0. So this whole thing will go to 0 because the denominator is getting bigger and bigger. So it's equal to 0. So what this means is that it is true. It passed the first condition. So now you can move on to the second condition. So what the second condition says is a sub n plus 1 less than a sub n. So is every term smaller than the term in front of it? So again, you're checking is a sub n plus 1 less than a sub n. Well, again, everywhere you've got an n, replace it with an n plus 1. So this would be 5 over 4 times, and in place of n, put an n plus 1 squared plus 3. And you want to know, is this less than or equal to 5 over just 4 n squared plus 1, or plus 3. Again, using the same logic we've always done. If this has got n squared, and this has got an n squared plus 1, then this denominator is always going to be bigger than this denominator. Therefore, the whole fraction is going to be smaller, and this will wind up being true. This term is, or this fraction is smaller than this fraction because the denominator is bigger. So this is true. So in this case, this series, it passed the first condition, it passed the second condition. If it's an alternating series and both these are true, you can conclude that the original series, this one up here, the original alternating series converges. So it looks like that. Well, so it converges. So it passed both parts of the condition. Now let's take a look at one more just to show you that these things actually can get a little trickier. And this next one looks like this. Now again, I'm still going to use the same rules. So I'll start by isolating it. There's the switch, and this part right here is going to be a sub n. But I think I'll do one thing first. Sometimes you can take advantage of some algebra to make it a little bit easier. This is an exponential, here 5 to the n, then I've got n plus 2 squared. Now just to make finding the limits a little bit easier, I'm going to change it into this. The summation from n equals 1 to infinity. Here's the switch, -1. And I'll make this be 5 to the n. And all I'm going to do is just expand this. So this is like having n plus 2 times n plus 2. So I'll FOIL it. That'll turn into an n squared plus 4n plus 4. So rather than writing as n plus 1 squared, write it like this. And again, the whole reason for that is just makes finding the limits a little bit easier. So in this case, this now is a sub n. So I go back to my rules. The first thing I want to do is to show that the limit to a sub n is equal to 0 if I can. May or may not be able to. But let's try that. So step number 1, again, try to show that the limit of a sub n as you go off to infinity is equal to 0. So in this case, we'll go ahead and put it right here. This will be the limit of, now the sequence is 5 to the n over n squared plus 4n plus 4. And this is as n goes off to infinity. Now this, you'll recognize, if n goes to infinity, the numerator is going to infinity, the denominator is going to go to infinity. So this is in case of infinity divided by finity, and hopefully you'll recognize that you'll have to use L'Hopital's rule on this. So the idea is this will be equal to the limit, and using L'Hopital's rule, you'll find the derivative of the numerator and the derivative of the denominator. Well, the derivative of the numerator, remember that's the 3-part rule. So if you have 5 to the n, the derivative of that, it's the natural log of the base times the original function times the derivative of the exponent, which is a 1. So that's just the rule for a to the x. And what this would be, the derivative of this would just be 2n plus 4. So you found the derivative of the numerator, you found the derivative of the denominator using L'Hopital's rule. So now try to evaluate it again. So still though, if you try to plug it in, you've got 5 to the n, the numerator is going to go to infinity. The denominator also will still go to infinity. So even though you applied L'Hopital's rule the first time, you've still got an infinity divided by infinity situation. So try it again. So if L'Hopital's rule fails the first time, try it a second time. So I'll go to the limit as n approaches infinity. And now I've got the constant in the numerator. I've got the constant natural log of 5. Now, when I find the derivative of this thing, it's still going to be the same part rule. Just of this term right here, it would be the natural log of the base times the original function times the derivative of the exponent. Now in the denominator, the derivative of 2n plus 4 is just going to be 2. So you applied L'Hopital's rule once, you applied it a second time. Now try it again. If you let n go to infinity, this time you've got a constant in the denominator. The only term that's got an n in it is this term right here. So as n goes to infinity, that's a constant, that's a constant, that's a constant. This term right here will go to infinity, and you've got infinity divided by 2. This will turn out to be infinity. So what this means is, when you ran through all this, you found that the limit of this thing, of the sequence, as you go off to infinity, was not equal to 0. So it failed the first test or condition. This is not true. Now again, from here, you know that it's not true. So at this point, you can't use, you just showed, since the conditions aren't satisfied, you cannot use the alternating series test. So you have to stop using the alternating series test. But again, you've showed this. Going back to the Nth Term Test to find out whether it diverges or not. Let's go back and take a quick look at that one again. So again, you actually show this. If you show that as you go way off to the right, if the terms of the sequence are not approaching 0, the whole sequence has to diverge. And you actually did that, so you'll have to switch at this point. So we'll switch from the alternating series test, which you cannot use, series test, to the nth term divergence test, which you can use. And you've actually already done it. You've showed that this limit is not equal to 0. It goes to infinity. And by the nth term divergence test, that tells you that the original alternating series diverges. So it's going to diverge. So the idea is if you try to find the limit and you do the first condition and it turns out to be something other than 0, this thing right here is not equal to 0, then this condition is not true and you have to stop using the alternate series test. So at this point, you can conclude that this series diverges, but it doesn't diverge by the alternate series test. It diverges by the nth term test for divergence. So you actually switch tests. So anyway, just be aware about that. And there's a couple more examples just to show alternate series tests.